Another draft physics video presentation. Still on the subject of photons, sort of. Mostly radio waves, microwaves, radar, light, that kind of thing. And how does it reflect? Pretty much. Scatter is just a form of reflection or transmission. And it's sort of important to understand that transmission can create what looks like scatter because it's diffusing the energy, spreading it over a surface. So it's not just about bouncing off something, it's about how something does different kinds of reflection in the sense that it takes energy in one way and it releases it in some other direction. Yeah, probably enough. Alright, so let's do some of this.
And to really understand the Mie scattering, we need to take a look at this chart. This chart reveals a lot about the principles of Mie scattering. Again, it is sort of...
So, alright, so he does this charting, but it doesn't really explain anything in any kind of, like why or how it works, because I think to do that, you'd have to concede their explanation is, silly. Their understanding of what a photon is doesn't make any sense. And, to describe things like reflections and such, you really have to understand, you have to understand it as a composite thing, this thing called a photon. So the argument is sort of, if you have a thing this size and you send light that has a wavelength, let's say twice as big as that thing, their theory is that this thing has to interact with this thing, and the fact will be is that even if you have a perfect reflection, that is, even if all the energy that hits this reflected back, it's going to reflect back not as this, but as something else. It's not going to be receivable as in the same frequency that it hit, or at the same, it's not going to have the necessary polarization to have the necessary frequency, so to speak, because the two are related things. It's annoying, the glare. So you can sort of understand that you have to hit. It's like if you wanted to see a photon, you'd have to hit a photon with something smaller than a photon. If you want to see something, you have to, the advantage of the light is that it's smaller than the thing you're hitting, so you have some chance of getting some of the stuff to reflect back perfectly. So with smaller wavelengths, then you have the hope of seeing something, because you're essentially sending more than one, but more than one of these wavy things, and you'll have the composite effect, that is one piece of this wave and one piece of that wave, and there's another wave and another wave, and pieces of them will come back and reform the wave that you sent. And so you have some hope of getting it back, and you have this hope of the whole wave hitting. The downside is that part of a wave can hit something, on either side, and the advantage is if you can get those pieces to come back, you have some hope of remaking a photon. But ideally you want to have the whole wave hit the object. Now the trick is that it'd be really easy to do this radar thing if you could just shoot light, little tiny frequencies, and just shoot a bunch of little tiny frequencies and get back your signal. And some advanced radars are doing that. Essentially they use lasers and other things that are pulsed at a frequency. So the light has a frequency, and then that frequency is being pulsed. So it's like there's a little bunch of little frequencies, and here is the light, and they pulse it, and they can get back their original pulse signal as a reflection and see something that way. The problem with regular radars is you have just a regular antenna, and again the polarization is really a function of how long it takes electricity to get through an antenna, a conductor, and so you're kind of stuck with the polarization being a function of how much time, how fast you can get stuff up the antenna. So if you have a long frequency, you have time to get to the top of the antenna, and if you have a short frequency, you don't have time, so the polarization is smaller and smaller and smaller, depending on how much time you have to get the energy through the antenna. The pulses have to, travel the antenna to be able to be emitted up here, and obviously this time it would take to get all the way up here to send a pulse is longer than the frequency. So, it's theoretically impossible to get the signal to come out more of the antenna. And the other important thing to understand is that the radar, you're trying to optimize it for its efficiency, and it takes a lot more energy. The higher the frequency, the more energy it takes to send it distances. So if you were trying to do radio by sending, by a light signal, you'd need an awful lot of energy to make the light photons, the high frequency photons, to travel the same amount of distance as the radio, the big frequency. So this stuff takes more energy, okay? And so when they're sending out radar, they don't want to have to send high frequency, because that's going to require a lot of energy to send the higher frequency, to have it bounce off a big surface, and that way get more energy back. So the optimum is to be able to spread your radar as wide as possible. That is, to use the energy to cover as much area as possible. And so you want to sort of optimize the radar frequency to the size of the object you're trying to see. So they'll use something that has maybe a 1 meter size, or 2 meters, to look at objects that might be 10 meters or 20 meters large. That way they're hitting the thing, they're hitting the object with something smaller than the object, so they have some chance of getting reflections back. And the reflections back are really going to depend on this surface. If this surface is all lumpy, okay, it's going to be a lot tougher, because you're going to get reflections in the wrong direction, a lot of them. And so you're really going to have to depend not on a photon being able to cleanly bounce off, but you're going to have to depend on being able to combine pieces of photons into a new photon that you're going to reconstruct out of the broken little bits that you're going to get from different places and such. But that's a mechanical description of what's happening, and like I said, their wave theory doesn't really fit, because how do you take this portion of the wave and this portion of the wave and rebuild waves? You're obviously rebuilding spatial orientations. You're rebuilding something by having different little tiny specks of it go in different directions. Well, obviously that direction is not very helpful, going in different directions, and just recombining the order, okay, that you had of the stuff you shot out. So you shot stuff with an order, and you're trying to get order back. And there's rules about how efficiently you can do that based on how big the polarization is of the light you're sending. So I can't quite see those two little lines. Didn't want to have to erase, but might as well. Poorly erased, but it's sort of erasing. Erase better. Well, it's doing the best it can. Apparently. So again, the idea is, if your object is, this big, you want to be able to send something smaller in polarization onto the object. And so again, their theory is that this thing is just some wave of stuff, some gradually on, gradually off, blah, 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 some kind of field perturbation. And there's no real sensible way to say that whatever it is, reflects off and some sort of likewise gradual way, and you end up putting these little bits of a wave back together at some location. It just makes more sense to understand that no, it's a quanta of energy, and each little piece hits a different kind of surface. And all you're trying to do is get these pieces back in the same phase, that is, lined up in the same time orientation. So if one's further away and one's closer, okay, that it's one wavelength difference, or two wavelengths or three wavelengths different, depending on how big the wave is you're hitting it with, then it's possible to get reflections that are out of phase, but in phase in the sense of their whole wavelengths out of phase, and therefore you can put the signal back together again and receive the reflection made out of the pieces of different photons. And their theory really doesn't work for that. And I think it's quite apparent that that's how it's working, though. That the photon you receive is made out of pieces of the photons you sent. Okay.
Particles that range roughly from about 1/10 the size of a wavelength to about 1 time the size of a wavelength, roughly speaking, for any incoming radiation. So when we talk about the radiation come from the sun, the light, then of course we talk about the particles in the air. But this can also be used for scattering, for example, for radar waves. When we send radar signals to targets such as planes in the sky, and we get the scattering back from those targets, we can calculate the kind of scattering we're going to get depending upon the relative size of the target, the cross-section size of the target, and the wavelengths of the radiation that we send to them. And you can see there is a range.
Yeah, well, you can predict it because of experiments that produce the results. They're not predicting it because they have a theory that predicts it. They have an outcome, and they have a mathematical way of formalizing the outcome in the sense that they know this is how it works because they've done it over and over and over again experimentally. The experiment draws these lines, not some known formula that revealed the truth.
Here, when the target cross section, as we call it, is roughly the same size, or somewhere between 1/10 to about the same size of the wavelengths of the radiation that we send there.
Kind of a huge difference, right? 1/10 to the same size is a huge difference. So obviously, if it's 1/10, that means you're hitting. Theoretically, you can have a cross section of 10 photons going across the thing, 10 waves, 10 thicknesses. And so you have some possibility of getting a sufficient amount of energy back. But it all depends, again, on the reflexivity of the surface. So we're back to like Newton's glass experiments where you just polish the surface and increase or decrease how much light you get reflected. And for big waves, you can screw them up just by making the surface irregular and making sure that there's no solid surfaces, like one flat surface that's bigger than a meter. So if you angle everything at different angles, you can so break the photons. The radar photons will hit and scatter in such different directions that there's no hope that you can put them back together, even if you can get them back on phase.
Then we're going to get this particular pattern of reflection or scattering back from the target.
So the pattern is really just made out of when you're doing whole photons. So if the thing is 1 inch across and you send something a ½ inch, then you can sort of understand that you've now created two multiples inside. So you can hit it with 2 photons across. But if you make it 1.5 inches or 1.25 inches, well, then you know that you're going to end up with a lot of broken pieces. And there's nothing to put those broken pieces back together because they're not going to reflect off something else. The likelihood is small. So the surfaces that you're trying to see, you have to send photons that are going to be capable of bouncing off those surfaces in whole multiples is what you're hoping for. And the more fragments you make, that cuts your likelihood of getting it back. And the closer you are to too big a wavelength, the less likely you are to be able to put them back together. So that's why there's this drop off on the whole multiples. It's just really telling you the size is a multiple of the size of the thing you're going to be detecting is a multiple of the wavelength. And so when you're on the multiple close to it, then you have a peak amount of photons you're likely to get back. And when you're off the multiple, that's all energy that likely won't help you at all, because it's going to end up just making broken photons, and that's it.
So it turns out, if we take a look at it, the vertical axis here really determines the ratio of the cross-section of the target, which is the effectiveness of the target scattering back the radiation, and the cross-sectional area of the target. So this is the scattering effectiveness of the cross-section divided by the actual size of the cross-section.
Right. So he's basically saying it's you're putting the wavelength into the size, and so it's two variables combined. So it's, you're not, the one side isn't telling you, well, that's wavelength or that's size. It's a combination of the relationship between those two things, and that's kind of automatically going to give you a curvy line, because the decimals are going to be the ones that are fractions of are going to end up down here, and the ones that are whole multiples are going to end up here.
So there's a ratio between them. And then on the horizontal axis, we have the ratio of the size of the target relative to the wavelength. So this can be a chart for any sort of radiation. So in the black letters here, I indicated an example where the target would be 1 meter across. So we talk about a really big object like a fighter aircraft or something like that. And
so 1 meter across obviously isn't a fighter aircraft or blah 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 blah, And again, you can tell from like the stealth bombers, the reason why they're angular is the very reason, is to prevent there to be surfaces that are larger than a meter. Any one surface, any flat surface that's more than a meter, square meter in size. And that's the whole objective, is to create a bunch of uneven surfaces so none of the reflections are in the same direction. None of them go back to the same direction, let's say. Terminate in the same direction. Maybe it's a better way to say it. So this is size over wavelength, and this is another version of that, which is, I don't know what the Q thing is, but anyway. But you get the idea. This isn't a standard graph in the sense that the graph is already graphing, So it's it's like taking two line graphs and pointing out where the lines intersect and creating a third graph that just has the intersections in it.
so here again, the target diameter is about 1 meter. And you can see then that the ratio of the size of the target to the wavelength then gets bigger and bigger, which means the wavelengths get smaller and smaller and smaller as we go from left to right relative to the size.
Right. So to understand the chart, it starts off with very big, gigantic waves. So, big things that would be tens or hundreds of meters or a mile. Obviously, you can't see anything with that radar unless it's the size of the moon or something. You can only look at a very big object because the wavelength is so large that the little thing that it's going to hit can't possibly send back a whole photon, because there's just not going to be very few coherent pieces coming back, and certainly they just won't be. You can't put back together photons that are that broken.
Size of the target, or relative to the size of the object that's doing the scattering. The red letters, they're related to something more in the order of visible light and the kind of things that you'll find in the atmosphere scattering visible light. For example, what if the particle is 1 micrometer in diameter, which is slightly larger than typical?
So, he puts this stuff in the red as if he's going to use the same chart to go 1,000,000 times smaller and talk about the same effect. So he's just basically arguing that, again, if I want to see a photon, I don't have something smaller than a photon to hit the photon with, so I don't have much chance of seeing a photon. I was just thinking about how much energy. I mean, theoretically, I suppose you could see something small, but yeah, obviously it's going to knock it over, or you could hit it with something the same size, theoretically, but yeah, you're not going to see it where it is. But anyway, so you have to understand that the chart starts off at at radio waves and is going towards light. So its light is where it starts to go flat. And it goes flat for the obvious reason that there isn't anything much smaller than, okay, there's not too many things smaller than visible photons, or high energy photons, as they're called.
Wavelength of visible light. So for both cases right here, that means that over here we have me scattering started with wavelengths of 5 micrometers, which is of course in the infrared, down to wavelengths in the ultraviolet range. So this really then scans pretty well the visible light, and you can see that visible light is scattered by particles of 1 micrometer in diameter in a very strange pattern, and we'll take a closer look at what that pattern means. Notice that the pattern...
Yeah, well, you've said that 3 videos now, and so we'll see if he gets to the closer look at what the pattern means. But he's going to turn it into an interference pattern, when it's really just you either put the photons back together or you don't. You have a bunch of broken pieces from photons coming back, and that's the only argument. There's no interference. There's either they're on phase and you can reconstruct them, or they're off phase and you have no hope of reconstructing them. So if they're coming from places that are more distant, so say if I hit the tail of with radar, and I hit the front of a plane with radar, and the radar's 1 meter, you can understand that the one at the tail and the one coming off the piece of the photon coming off the front would have to be whole multiples of a wavelength in distance for you to have any hope of reconstructing them. If it's more or less than a whole wavelength, whole meters, and if it's 9.7 meters to the tail, then you're going to end up probably having a hard time putting the photons back together than if it's 10 meters exactly. So it's just the fact that you have to, if you don't put the phase back together, you have no hope of putting the pieces back together. The pieces are useless if they're out of phase. That's the simple takeaway point.
Tends to diminish as you go further out. And then here we get into what we call optical scattering, which is simply particles being so large that the wavelengths of visible light scatter in all directions depending upon the direction of the side of the particle.
He just means by the particles being so large is that everything's larger than, just about. So you're having lots of little pieces flying off from lots of different photons, and this isn't going to matter anymore.
All right.
The phase differences are going to be a million-fold phase differences from just a tiny sized object. Will have a million phases in it. There's a million wavelengths in something an inch long when you're sending ultraviolet light. So obviously there's kind of a normalized number that will be on phase versus off phase.
Now, let's take a look, for example, on radar technology. Let's say that we have an object, like a fighter aircraft in the sky, and we want to send a radar signal to that fighter aircraft to try and detect it. Well, you can see that for a certain cross-section size of the target, there's tremendous variation in how much scattering we're going to get back. So, for example, if we pick a wavelength of the radar in such a...
All right, another thing to say is this isn't going to 0, it's going to half as much getting back, so it's not like it goes to 0. And all you're trying to do is make it optimum. And again, it takes more energy the further towards visible light you go, the more energy it takes to cover area in space. So you have to send a lot more radar out at the higher frequencies. The obvious answer would be just use the higher frequencies because there's less variation. But the downside to using the higher frequencies is you have to produce a very dense radar that takes a lot of energy.
That the scattering coming back is in this region right here. We don't get a lot of energy back, and it would be very difficult to detect that target. We want to catch it at a lope like this, where we get a much larger percentage of the energy we sent to the target scattered back. It turns out that the Russians in the early technology of radar invented a radar that had a frequency range from 145 to 175 megahertz, which meant radar signals from 1.7 to 2.1 meters. So what that meant was that the wavelengths of the radar signals being sent were such that they took advantage of the principles of Mie scattering, that they would get a very large percentage of the energy sent to the aircraft scattered back, and so they would much more easily detect that aircraft than if they had sent wavelengths of a different wavelength that may not have done the job as well.
Right, just basically saying that that's a nice size for detecting the average size airplane, because there's surfaces that'll end up, giving them not only pure reflections, that is where the wave reflects right off the surface, in the sense that all the photons have all the little quanta have a chance of reflecting back because there's enough surface to hit. But besides that it's optimized in the sense that the different photons will hit different areas and have a higher chance of reflecting back. But it's more, like I said, the price you're paying for it is that it's harder, it takes more energy to produce a radar that you don't have to point already somewhere where you know it is, because if you try to point it everywhere to broadcast the radar wide, it would take too much energy.
Same for visible light. You can see that visible light will have certain peaks of scattering when the wavelength relative to the size of the particle is of a certain size. And you can see that it increases, diminishes, increases, diminishes, increases, diminishes as the frequency increases as the wavelengths get smaller.
So the humps just represent the fact that if your wavelength is the same, is a multiple of the size of your object, you have a higher likelihood of getting the photons back without breaking as many that are unrecoverable. So you're making more pieces that are possible to reconstruct.
Smaller and smaller. Now eventually, when the wavelengths become really small relative to the size of the target, or relative to the size of the particle in the atmosphere, you can then see that the scattering does no longer really depends upon the wavelength of frequency. The amount of light being scattered simply will be relatively a constant, and so that would then be the ratio. Then would be a 1-to-1 between what we call the cross section of the particle, which is the effective scattering back of the particle, divided by the actual size of the particle. So when that ratio becomes 1, that's when we get into what we call the
cross section divided by the actual size. I don't know. That's a strange. I don't know what he means by that exactly. The cross section versus the actual size. I don't know.
The optical region. So this is the Mie region, where we have that large variation that diminishes when we go from large wavelength to small wavelengths, and then we get into the region where it's pretty well a constant. Before that, when we have Rayleigh scattering, notice what happens. That the cross section, the effectiveness of the particle in the atmosphere scattering out the light in the form of Rayleigh scattering, depends upon pi r squared, or it's basically a ratio of pi times r, which is basically the cross section of the size of the particle divided by the wavelength to the 4th power. Now, a better way to say it is it's a ratio of the size of the particle relative to the wavelength. And notice that as the size of the particle increases relative to the wavelength, you have a tremendous increase in the ability of that particle to scatter light. So it's like a linear relationship. And so therefore,
right, and it's just sort of just pointing out the fact that obviously you have no hope if your particle, pretty much no hope. Okay, if your wavelength is bigger than the particle size, then clearly it's going to be really hard to have a photon reflect back, because it's always getting broken. There's no such thing as an actual photon hitting the surface, because every single one of them misses. Parts of it miss.
Well, it's not really linear because it's a logarithmic scale, so it's not quite linear. It's a curved scale, but you can see, though, that as the r becomes big relative to lambda, that the effectiveness of scattering increases tremendously. You can see this is a logarithmic scale right here. So that gives you pretty...
Yeah, so he probably is conceding that he probably didn't draw that right, because that line probably slopes this way. It's rapidly increases once you're starting to get to the size of a photon. Once the size is reaching the same size as the object, then you're going to get an increase. And the rest of these humps are just multiples of the size of the object. So you're just saying this one, the wavelength and the size of the object are the same. This one, it's twice as small. The wavelength is half the size of the object. This one, it's 1/4 the size of the object, and so on.
The idea of how photons are scattered in the atmosphere, and how photons generally, regardless of any wavelength, be it radio radiation, be it well, that would be kind of in the radio frequency right there, or be it visible light, or be it infrared or ultraviolet. You can see they all have the same scattering principles, all dependent upon the ratio of the size of the particle to the size of the wavelength. So regardless of the size of the radiation, the size of the photons, the relationship between the size of the particle that scatters and the size of the wavelength that's being scattered, that will determine the kind of scattering that you will experience.
So that obviously didn't make any sense. You started off by saying regardless of the wavelength, and then you said, well, it's clearly dependent on the size of the wavelength and the size of the particle. So it's just what I just said. So the first hump is the wavelength and the particle are the same size. The second hump is they're half multiples. Third, go down. And it's really about the size of flat surfaces, or surfaces that are able to produce a consistent reflection. And so you have to add that into the equation. And such. And then you can make surfaces that don't reflect well because they diffuse everything that hits them, so they're not going to send anything back, coherently. Because you put a bunch of facets on the surface, and the facets are going to make it more difficult for you to reflect light coherently back, photons, especially big wavelength ones. Yeah, so that's enough. All right, so till the next time and such, keep it shorter. I probably should make a little video on magnetism since I have one to do, so maybe I'll do that also today at some point and such.